Welcome, this is Dr. Plague. Now, for this video I had to think a little about what I wanted to include. What I've decided on is to develop a simple assembler for the Plague Mark II, and then demonstrate a simple script to program the output from the assembler into a flash chip. I've decided to wait until the next video to write any test code to assemble and run on the Plague Mark II. That way, those that aren't interested in the assembler itself can continue on with the next video and still see the test code running on the homemade CPU. Now, like I've mentioned, this will be a very simple assembler, not capable of much, but it will get us started. It won't be anywhere near as capable as the assembler that I've developed for the upcoming Plague Mark III. The Mark III assembler is a full-fledged macro assembler that will be able to handle multi-file projects. It also assembles macros and allows labels by creating a symbol table. It also supports a number of dot directives. The Mark III assembler creates several output files including list files, binaries, and hexadecimal code files, among others. The simple assembler I'll be creating in this video will only output one file, which can be used to either manually program a flash chip, or it can be sent to a script for programming. The source file that will be sent into this assembler will have a very strict format to help simplify writing the code for this assembler. Now, I wouldn't normally have a strict format like this for the input source file, but I wanted to write this entire assembler in one video, so I need to make some sacrifices. We can place comments in the source code by preceding them with a semicolon. They can be placed on a line by themselves, or after a line of code with at least some white space between the code and the comment. Each line of code needs to start with the address in memory where the instruction will reside, followed by the assembly language mnemonic for the instruction, then any operand that relates to the instruction. Also, all addresses and values must be decimal for this assembler. No hexadecimal allowed. And that's pretty much it for the format. The output file from this assembler will also be very basic. It'll just contain the binary machine code value along with the address it resides at for each instruction. I'll show it to you a little later. To create this simple assembler, I'll be writing it in the language of C, and I'll be using the Pelles C IDE, which is free to download and use. I believe the most current version is 13 as of the date of this video, but I have an older version installed, version 9.00.9. Any version should hopefully work fine, but there may be some differences in the IDE. Okay, let's get started on writing this assembler. I'm going to start an empty project and choose a console program. And I'll choose 64-bit, although 32-bit would work fine too. I'll name this program MK2-PASM for the Mark II Plague assembler. Then I'll create all the source files. I'll choose to create a main file, assembly file, with header, and a feedback file with header for reporting errors to the user. I'll add some include guards to each header file, so they're only compiled once. And let's add a comment to the main file to identify this program as an assembler for the Plague Mark II. Then I'll include the headers in each respective C file. I'll also include both headers in the main file so I can call functions from either of them. I want a way to report errors to the user, and I want to keep track of how many errors there are, so I'll create a 32-bit value for that. I know that 32 bits is overkill for this assembler, but it's what I generally use for most generic variables. I'll add this as an external variable in the header file, and I need to include the standard int header file for this variable type. When we run this program, I want it to identify itself as the Plague Mark II assembler, and give it a version. Normally I wouldn't hardcode the version number in a printf function, but I'll do it for this simple assembler. Then I need to include the standard I/O header file for the printf function. I'll be sure to print out the number of errors found. Let's create a function to allow us to print out each error as it is found. I'll call it error, and I'll make it a variadic function, hence the 3 dots. This will allow us to call this function with any number of variables, much like how the printf function works. The error message will be passed into the message variable, and the arguments will follow with the 3 dots. And I'll place the prototype in the header file. I'll create a pointer to the arguments of type VA_list. Now, to create a variadic function, I need to include the standard argument header file. Then, I'll point our argument pointer to the list of arguments after the passed-in message. I want to create the formatted message using the passed-in message and the arguments. I'll use VAS_printf for this, and I'll need to create a pointer to the formatted message. The VAS_printf function will allow us to dynamically allocate enough memory for the message using the passed-in arguments, and I'll just include the standard I/O header file for any of the printfs. Now we need to define a library extension in order for VAS_printf to dynamically allocate memory, and I'll assign it the value of 1. And let's be sure to clean up after ourselves. I want to deallocate the memory for the formatted message and free up the variable argument list. But before we clean things up, let's print out our formatted message and let the user know the error number after incrementing the error value. Beautiful! Our error reporting function is now complete. Let's test out this function to see how it works. Before we print out the errors, I'll call this function a couple times. I'll just print out a message that says, "This is error test number %d period." I'll use number 1, then I'll call it again with the number 2. Okay, let's compile and run this. And it works just fine, and it reports 2 errors as expected. Okay, let's delete the test calls. Now let's get the file name for the assembly language file. If the program is called with the file name, we'll copy that argument into the file name variable. Else, I'll prompt the user for the file name. And I need to include the string header file to work with string functions. Now that we have the file name, let's create the function that'll assemble the file. I'll fill in the code in a bit, and I'll place the function prototype in the header file. Let's let the user know that we're assembling the code and call the assemble function. Before I forget, I'll wait for a key press before ending the program, so when it's run as a standalone, we can read the output before it closes. Now that's it for the main function. Let's go on and write the code to assemble the input file. I want to write this assembler in a way that'll make it easy to add more assembly language instructions in the future. So I'm going to create a structure of information for each assembly instruction. The information I want included is the mnemonic for the instruction, which I'll make 6 bytes in length. This will allow up to 5 characters and the null terminator. Then I want an 8-bit opcode and the operand type. And by the way, I need to include the standard int header file for this. Now, for the operand types, I'll create 3 of them. NA for non-applicable. These will be assembly instructions that do not have an operand. Address for instructions that have an address for its operand. And immediate for immediate operands. Now, I'll create an array of instruction info. Looking back at our CPU instruction format that was created in previous videos, we have NOOP, which has an opcode of 0, and no operand. So let's add that to our array. NOOP 00 hex for the opcode, and NA for no operand. By the way, the lower nibble of each opcode will always be 0, and the operand type will allow the assembler to change that nibble. Add has an opcode of 1 and has an immediate operand. So I'll add in add with 10 for the opcode and an immediate operand. Out's opcode is 2 with no operand, so let's add that in. Jump if not carry has an opcode of 4 with an operand consisting of an address, so let's add that. Then halt's opcode is 8 with no operand. There, that's all the info the assembler needs to assemble the source file. I do want to define the max number of instructions, and we can calculate this out using the size of the array divided by the size of the structure. Now, in the future, if we ever want to add more assembly instructions, which we will, then we don't need to change the assembler other than to add the new instructions into this array. Sometimes I see people writing assemblers by using a long string of if-then-elses to individually handle each different assembly instruction. This is something I don't want to do, hence the reason for making this instruction array. So now, let's open up the source input file for read-only using the file name, and print an error if it's unopenable. Then I'll create the file pointer here, then include a couple header files for file operations and error reporting. Let's make sure we close the input file when we're done. We also need to open one more file, the output file, for write-only. I'll use the source file name and just append a txt extension to it. Of course, we want to output an error if we can't open the file. Then close the input file and exit. And I need to include the string header file to use the string concatenation function. Let's not forget to create the output file pointer. And close the output file at the end. Let's now loop through every line in the input source file. And I'll place each line into a character array named input line, which I'll create up here. I want to tokenize each line, so I'll create a pointer for the tokens. Now, I'll get the first token of the current line using a function named stringToke. Normally, I wouldn't use this function in a real assembler due to its limitations, but it'll work fine for this simplified assembler. The stringToke function will return a pointer to a token that it found, using any character in the separator string, of which I've included a space, a tab, a new line character, and a carriage return character. This means it'll search for tokens separated by those characters. The problem with this function is that it alters the input string by adding a null character in place of the ending separator, which is one reason why I wouldn't normally use this function. So now, token will point to the first token. I'll make sure that the line contains some type of text that is not a comment. If it is a comment, then we'll continue on to the next line. And you know what? We need to include the standard library to define null, which I forgot previously. Now, the first token of each line that is not a comment must be an address for the instruction that follows. So I'll make sure the token starts with a digit. If not, we'll output an error. I need the C-type header file included for the isDigit function. Now, I'll create a variable to hold the address, and it'll be just 8 bits. Then I'll get the address using the ASCII to integer function, which is part of the standard library that I already included. Let's make sure the address isn't out of range. I'll print an error message if it is. And I'll define the memory size right here. Remember that the Plague Mark II CPU can only access 16 bytes of code. Now I'll retrieve the second token, which should contain the instruction mnemonic. If it's missing, then I'll print an error. I'm going to create an instruction variable that'll hold an index into the instruction array that we created earlier. I'll create a new function that will search for the instruction within the instruction array. The token containing the assembly mnemonic can be passed into it. Then I'll just place the prototype up here. I'll fill in the code in a bit, but first I'll call the new function to get an index into the instruction array. I'll make sure we found a valid instruction, else print out an error and continue to the next line in the source code. Let's add the code to the find instruction function. I want to make sure the instruction is in uppercase, since I've added all the instructions in the array as uppercase. I'll search through all the instructions in the array to see if we have a match. I'll use the string compare function to do this, and I'll return the index if the instruction is found. If there is no match, then I'll just return the value pertaining to the maximum number of instructions. I'll create a variable to hold the binary value of the machine language instruction. Then I'll grab the opcode from the instruction array using the index that we found. Now I need to find out if there should be any operands. Any operand for this CPU will contain a numeric value, so I'll get another token for that. I'll make sure the operand exists and that it is a digit, else I'll print out an error. I'll make sure the operand is within the range 0 through 15, else print an error. If it's within range, I'll add it to the binary code, since the operand will be in the lower nibble. Finally, let's print the assembled source code line to the output file. I'll print out the binary value and the address that it gets placed into, both in hexadecimal. Let's compile it. Good, no errors. And that's it. This completes this very simple assembler. Not much to it, I know. Okay, let's test this assembler out. I'll create a new assembly language source code file named test.asm. And open it up. I'll first test all the instructions with some comments. Now let's assemble this by hand to make sure we know what the correct output should be. I'll write this in hexadecimal. Halt is 80. No-op is 00. Out is 20. Add is 12, since the operand is 2. And jump if not carry is 41, since the operand is 1. Let's assemble this and look at the output file. There were no errors, which is good. And if we compare the output file to our hand assembly, we have 80 at address 0, 00 at address 1, 20 at address 2, 12 at address 3, and 41 at address 4. Perfect! Let's add in some errors to test out the error reporting capability. Halt. Can you see the error? There is no address before it. 16 out. This has an address that is out of range. It can only be between 0 and 15. 5. I've added an address with no instruction following it. 6. Move 0. There is no such instruction for the Plague Mark II CPU. 7. Jump if not carry. I forgot to add in the address to jump to. 14. Jump if not carry 16. I added the address, but it isn't between 0 and 15. Now let's assemble this to see if it catches all the errors. And it did. Beautiful! Okay, and now we could use this output file to manually program the code into a flash chip. But wouldn't it be nice to automate this process? We could create a script to do this. I'm going to write a simple Teraterm script to program the flash chip using my homemade flash programmer from some previous videos. If you're not familiar with Teraterm scripts, you can go to the index under the Help menu and look at all the commands under Macro Help. Here's the simple script that I've created. I'll go through and explain it. Here I've set a timeout period for 1 second. This will be used for any waits or receiving of lines. Here I get the input file to program into the flash chip. I open up a file select window and set the result to no file selected if none was selected. At the end, I display a message window with the result. If a file was selected, then I open it and mark it so I can move back to the beginning at any time. I call a subroutine to program the flash chip. Then call a subroutine to verify the contents were properly programmed. Then I close the file. Okay, let's look at the program subroutine. I've created a do loop to go through each line of the input file. I read in each line into a variable named line, and break out of the loop if we're at the end of the file. I copy the address out of the current line and place it into a variable named address. Then I send a command to my homemade flash programmer to set the address and wait for a prompt. Remember, we set the address by outputting an A followed by the address. Then I do the same thing for the code or data byte. We output a W followed by the data byte to program into the flash chip. And that's it for programming. Let's look at the verify subroutine, which is optional. I first set the end result to passing. I'll change it if we come across a fail. I move back to the beginning of the input file. Then I send commands to my homemade Flash programmer to dump out the first 16 bytes. I wait for the last command before reading in the line containing the 16 bytes. This output from the Flash programmer will go into a system variable named input_str. I set the errors to 0. I'll set it to 1 if any errors occur. Then I create a do-while loop to go through each line in the input file. It'll break out if there are any errors. I'll read in the current line and break out of the loop if we reach the end of the file. I get the address from the current line and insert a 0x so I can convert the string to an integer. I'll store the integer into a variable named int_address. I read the data byte from the current line into a variable named data. Now I calculate the index into the input string. Since I separate the 16 bytes between each group of 8 bytes, I determine if I need to account for this by adding 2 to the position if we're looking for bytes from addresses numbered 8 or above. Then I get the data from the input string based on the position that I've calculated. I compare the read-in value to the value that should be programmed in, and create an error message if they don't match, along with setting errors to 1. And that's it. This script should allow us to automate the programming process. Let's try it out. I'll write the assembly source code file for the last program we wrote and tested in part 2 of making the Plague Mark II CPU. This should give us 15, 40, and 80. Let's assemble it. And we get the correct machine code. Now I'll take the flash chip out of the Plague Mark II, and it should already have this code in it. Sure enough, it does. I'll erase it and verify that it is erased. Now let's run the script. To do that, I'll select Macro from the control menu. Then I'll select the file to program in. The script finished and the verification was successful. And we can see from the dump that the code was correctly programmed in. Beautiful! Well, that's it for this video. We've successfully created a very simple assembler and tested out a script that allows us to automate the programming process. Keep in mind that if we're programming large amounts of data into a flash chip, I wouldn't use a script like this since it's a very slow programming method. At some point, I'll make future videos on speeding the programming process up. In the next video, however, we'll write some code in assembly language for the Plague Mark II CPU and use these tools to program and test out the code. Thanks for watching, and I'll see you next time, right here on Dr. Plague.